Imagine floating just a few million kilometers away from the sun. You are looking at an enormous ball of plasma, roaring at roughly 5,500 degrees Celsius, constantly releasing an unimaginable amount of energy outward. Yet, just a short distance from that raging inferno, the vacuum of deep space sits at a freezing -270.4 degrees Celsius, which presents a rather obvious contradiction. How can a massive star emit millions of degrees of heat from its core, yet fail to warm up the empty space immediately surrounding it? Pop culture loves to portray this void as an aggressive, instantly lethal freezer. If you take off your helmet, the cold will immediately turn you into a solid block of ice. But the vacuum doesn't work that way. To understand what is actually happening out there, we have to throw out everything our earthbound instincts tell us about what temperature actually means. On Earth, heat is the kinetic energy of microscopic matter. For temperature to rise, you need vibrating particles slamming against your skin, transferring energy. But interstellar space is almost entirely empty, holding only a tiny handful of particles in a single cubic centimeter of void. Without enough matter to bump together, the familiar processes of conduction and convection completely fail. A hot object cannot heat the air around it if there is no air to heat. Space isn't actively sucking away warmth like a cosmic refrigerator. It simply lacks the physical matter required to hold thermal energy. Without an atmosphere to carry its heat, the sun cannot operate like a giant furnace. Instead, it fires its energy outward exclusively as electromagnetic radiation. Unlike conduction, radiation doesn't require physical particles to bump into each other. It consists of photons that can travel perfectly intact through an absolute vacuum. It is like sending a tightly sealed message across an empty room. The pure energy travels straight across the distance invisibly, without altering or warming the room itself. As those photons travel further away from the star, they spread out over an increasingly large area, reducing the intensity of the solar energy you'd receive. The sun isn't trying to heat the universe. It is a cosmic broadcaster, firing raw, untouched energy through an endless void. Bright shifting tone. The situation changes the moment that broadcast finally hits a physical object. When electromagnetic radiation strikes matter, the object absorbs the energy, causing its internal atoms to vibrate and generate heat. Take Mercury, the planet closest to the sun. Direct solar radiation blasts its sunlit side, driving the surface temperature up to roughly 430 degrees Celsius. But because Mercury has an extremely thin atmosphere, it cannot redistribute that warmth. The moment the surface rotates into the darkness, it immediately radiates its energy away, and the temperature plummets to -180 degrees. This creates an extreme balancing act for spacecraft and astronauts. A spacewalker can be absorbing blistering heat on the side facing the sun, while simultaneously freezing in the shadows on their back. Without an atmosphere to mediate, temperature in space becomes a highly localized phenomenon. It depends entirely on whether or not you are standing directly in the path of the star's radiation. Ultimately, the temperature of anything floating in space relies on a constant equation, absorbing incoming solar radiation and radiating excess energy back out into the dark. That incoming energy undertakes an incredible journey. A photon escapes a blazing star and travels at the speed of light for roughly 8 minutes and 20 seconds. It crosses 150 million kilometers of freezing, empty void without being altered, deflected, or drained. Then it finally crashes into the atoms of human skin on Earth. The energy is absorbed, the molecules vibrate, and the radiation transforms instantly into heat. So the next time you step outside and feel the warmth on your face, you aren't feeling the empty space above you. You are physically interacting with the raw energy of a star.